Video will review Chapter 18. If we have a reaction and only start with reactants, then the forward reaction going towards products will start off at the fastest rate it will ever be at. As those reactants are consumed, the forward reaction will decelerate in terms of its rate, and the reverse reaction, starting with no products going back towards reactants, will increase in rate until at some point the equilibrium will be achieved whereby both reactions will be happening at the same rate. At that point, the reactant and product concentrations may not be the same, but they will not change. Equilibrium has been established whereby the concentrations of reactants and products do not change any further. And the relative amounts of reactants and products depends on what the reaction is and the conditions that the reaction is occurring under. Next, we have the equilibrium constant, which for any reaction is essentially the concentrations of products over the concentrations of reactants. If there's a coefficient in front of any substance, then that will become an exponent in this equilibrium expression, K, and K only considers gases and aqueous solutions. Any solids and liquids should be omitted from the expression. Every reaction has its own value of K, but that value of K changes with temperature, and only temperature. It doesn't matter what concentrations of reactants and products you start with, always the system will progress in the direction of satisfying K. If you have a K that is much greater than 1, that means that you have a lot of products over not many reactants, and therefore the reaction favors the products. If K is much less than 1, it means you have not many products over many more reactants, meaning that the reactant side is favored. We know that K is a destination. It's essentially where the reaction goes towards. However, you can always test to see where you're at relative to where you're going by finding Q, the reaction quotient. It's calculated in exactly the same way, and if Q is equal to K, then it means that your system is at equilibrium and there will be no further change. If Q is less than K, you have not enough products over too many reactants, and so the system will progress rightward, consuming reactants and forming products until you satisfy K. If Q is greater than K, it means the system has too many products over too few reactants, and the system will have to shift leftward until K is satisfied. If you're ever asked to determine the equilibrium concentration for a reaction, you should use an ice table. Mathematically, an ice table may require the solving of a quadratic or a cubic, but you'll never face that in this class. For practice with ice tables, I have other videos that I would refer you to. On to Le Chatelier's principle, which simply states that if a system at equilibrium is changed, the system will react by opposing whatever that change might be. So if a reactant is added, the system will shift rightward to consume some amount of that added reactant and produce some product. We see that in the equilibrium between H2I2 and HI in this chart, wherein the H2 reactant is increased at time t equals 10, and the system responds by consuming some of it and consuming some I2 in order to produce HI. Some tips with Le Chatelier's principle. One is that you should treat heat as a reactant or product. Changing temperature will affect K, and if heat is absorbed by a reaction, then it's essentially a reactant, and if heat is released by a reaction, it's essentially a product. If a reaction releases heat, and you raise the temperature, that will cause the reaction to shift leftward because you're essentially adding a product, and K will decrease in value as the system shifts leftward. For any changes in volume and pressure, the system will shift towards the side with more or fewer moles of gas. Lowering volume causes an increase in pressure, in which case the system will respond to decrease the pressure, meaning that it will shift towards the side with fewer moles of gas. A principle that often is confused is that catalysts don't actually shift your equilibrium position, they only affect how fast the equilibrium is reached. Additionally, adding an inert gas does not actually affect the equilibrium since it doesn't participate in the reaction. That's all for this video. I hope it's been helpful. Feel free to leave any questions or comments in the comments section below, and thanks for watching.